Assalamualaikum and good day. My name is Siti Nur Syafiqa E23A2579. My metric number is E23A2579. I'm from the Bachelor of Applied Science in Geoscience. Today, I will be presenting my mini research project entitled Geological Mapping of Groundwater Potential Zone in Tanah Merah. The first one will move to introduction part, which is the first one is background of study. So groundwater is a key part of the water supply system in Malaysia, particularly in rural areas where surface water is unreliable or unavailable during dry seasons. So in this research, I focus on Telaga Bijih in Tanah Merah, Kelantan, a region which is a crustal bedrock that stores groundwater primarily in second features like fractures and weathered zones. Since these features are not visible, apparent, or uniformly distributed, I apply GIS and remote sensing to analyze terrain feature and URI to subsurface validation. Second, we'll see on problem statement. It is difficult to identify groundwater in crystalline rock due to irregular and hidden fracture zones. Traditional exploration methods such as random drilling or relying solely on geological intuition often result in failure and financial loss. So this problem arises because the rock in the study area lack natural porosity. Instead, groundwater collects in unpredictable space created by weathering and fracturing. So this study is guided by three main objectives, which is the first one is to develop and assess thematic layers using remote sensing and GIS for the identification of groundwater potential zone in Tanah Merah, Kelantan. Second is to develop a groundwater potential zone map through the integration of spatial parameters into weighted overlay analysis using GIS. And lastly is to validate the predicted groundwater zones using electrical resistivity imaging to identify subsurface saturated and fracture zones. Next is scope of study. So this study focused on Telaga Bijih, an area covering approximately 25 square kilometers in Tanah Merah, Kelantan. The research also utilized supplemental data from neighboring areas such as Macam to enhance geological interpretation and comparison across similar terrains. Next is significance of study. The study promotes a more cost-effective and reliable method of groundwater exploration in hard rock terrains by combining GIS and ERI techniques. The last part for the introduction is a study area. So the study area of the Telaga Bijih is found at latitude of 5 degree 45 minutes north to 5 degree 48 minutes north and longitude of 101 degree 56 minutes east to 101 degree and 59 minutes east. So the site is characterized by a tropical climate with an average temperature ranging from 30 degrees Celsius to 35 degrees Celsius. To begin the literature review, we first recognize the importance of groundwater, especially in rural Malaysia setting like Kelantan. During dry seasons, surface water become unreliable, making groundwater essential. However, locating groundwater in a hard rock terrains like granite is challenging because aquifers are not visible at this surface. As a solution, recent studies have turned to advanced technology like GIS, remote sensing, and electrical resistivity imaging, which allow for efficient, non-invasive exploration of these hidden water zones. In crystalline terrains such as granite and metamorphic rock formation, groundwater does not flow through the rock itself, since it is naturally impermeable. Instead, it accumulates in secondary structures like cracks, fractures, and zones that have been altered by weathering. GIS and remote sensing are powerful tools that allow researchers to create thematic maps showing surface features like slope, drainage density, land use or land cover, and especially linear patterns, which are often signs of fracture or faults. Previous study by Bhattacharya and Reddy, Gupta and Sulaiman have shown that areas with high number of lineament and low slope gradients tend to accumulate more groundwater. So URI is a geophysical method that provides a look beneath the surface. It works by sending electrical currents into the ground and measuring how the resistance the subsurface materials offer. Water-based zones such as saturated fracture or weighted rocks have low resistivity values, usually between 10 and 800 ohm meters. So this method has been proven effective through study like the one conducted by Sulaiman in Kemahang, Kelantan, and another by Riwayat in Johor, both of which successfully identify aquifer zones using ERI. So the final part of the literature reviews discuss the Benefit of integrating surface and subsurface approach. If these two methods are used together, they significantly increase the accuracy of groundwater detection and reduce the risk of drilling in dry areas. So next, for the resource flowchart, we have two resource flowchart, which is the first one is remote sensing and GIS flowchart and ERI flowchart. For the remote sensing and GIS flowchart, first we have to do the literature review and then collect the data, which is satellite imagery and GEM analysis. And then we have to do a thematic layer generation, which is F6, which is lineament density, drainage density, slope, land use, hydrology, and geomorphology. And then we have to reclassification and standardization, which is we have to reclassify into 5 class and standard value 1 to 5. Next, we have to weight overlay to produce groundwater potential zonation map. And lastly, we have to do conclusion and interpretation. Next is ERI flowchart. We have to do first is literature review and then GIS-based site selection. After that, we have to prepare for the fieldwork, which is have urban telemetry LS, electrode, and also cables. After that, we have to collect the ERI data. We have to set up pool depot area, 200 meters length with 41 electrode with spacing 5 meters. Next is resistivity data processing. Just have to input data into RES to TINV software and also generate 2D subsurface resistivity profiles. After that, we have to interpret our result, which is less than 100 ohm is for saturated or fracture zone and more than 1000 ohms is for the dry bed rocks. And then we have to overlay your result with this GIS map. So next, we will move to the methodology. So in this study, I apply a mixed method exploratory design, which means I combine both spatial and field-based methods. On the surface level, I use GIS and remote sensing to analyze terrain characteristics like slope, land use, and geological structures. Then I validate this prediction using ERI to see what's happening beneath the ground. By integrating these two approaches, the study aimed to more accurately identify and map groundwater potential zone in the hard rock environment of Tanah Merah, Kelantan. The first step in my methodology was geological mapping. From this map, I identified key features such as lithology, fault lines, and lineaments, which are essential indicators of groundwater movement and storage in crystalline rocks. In the GIS and remote sensing phase, I used satellite imagery from Landsat 8 and Sentinel-2 along with SRTM digital elevation model data. So this source allow me to extract 6 important thematic layers, which is the first one is slope, then drainage density, land use or land cover, lineament density, lithology, and also geomorphology. So each of these layers plays a role in groundwater movement and recharge. I then reclassify each layer into 5 suitability classes, ranging from very poor to very good, using the analytical hierarchy process (AHP). I assign weight to each layer based on its importance and perform a weighted overlay analysis in ArcGIS. This process results in the generation of the groundwater potential zonation map, which visually highlights areas with varying groundwater potential across the study site. Once the GIS analysis highlights the high potential groundwater zones, I select those locations for further verification using ERI. I conduct 200-meter surveys lines using the per depot configuration with 41 electrodes spaced at 5 meters apart. The camera used was the urban telemetry LS, which sent electrical current into the ground and measure the subsurface resistivity. Finally, this ERI result will overlay on the GIS map, allowing to confirm and fine-tune the location of groundwater zones. Lastly, we will see the expected result. At the end of this research, the main output will be detailed and reliable groundwater potential zonation map, especially for the Telaga BG area. This map is developed by integrating both surface indicators like slope, lineaments, and land use from GIS and remote sensing, and then validating those predictions using ERI data collection in the field. In particular, the zone with the best groundwater potential are expected to show a combination of low slope, which promotes infiltration, high lineament density, indicating fracture zone, low drainage density, which reduce runoff and permeable land cover, such as vegetation or open soils that allow water to seep in. This area should also show low resistivity values below 100 ohm meter in the ERI result, which will confirm the presence of saturated and fractured rock underground. So thank you for your attention. Assalamualaikum and have a great day.